Greetings physics students, this is Mr. Stockbridge. I thought we would go ahead and switch things up a little bit and do a video instead of a traditional PowerPoint this time. So let's go ahead and we're going to talk about gases. We've already covered solids and liquids earlier in the week. Remember that gases, simply put, this is when the molecules are quite far apart. If you compare the size of the atom or the size of the molecule to the distance between them, the distance is quite large, and that wasn't true of solids or liquids. Now, there are some ways in which gases are similar to liquids. Like liquids, gases are going to take the shape of whatever container they're in, but what makes them different is that liquids, remember, we couldn't really compress those, but gases can be compressed quite a bit because there's so much space in there. We're going to dig a lot more detail into that here in just a couple of minutes. The thing that makes a gas ultimately comes down to the energy involved. The individual atoms and molecules in a gas are moving at much higher velocity than they were with either solids or liquids. The result is they aren't really bound to each other in the same way. Because of the higher velocity, that's going to result in a higher kinetic energy per particle. And as we'll see next week, internal kinetic energy is just a fancy way of saying temperature. So gases occur at higher temperatures, higher energy settings than liquids or solids typically do, depending on your material. The big thing about gases is, like I said, they are highly compressible. Now this has a lot of interesting implications, some of which you're going to be familiar with, and some are going to be probably quite different from what you're used to. So for example, you wouldn't live for very long if you were all of a sudden on the top of Mount Everest or in an airplane and all of a sudden a window breaks and the pressure drops in the cabin. That's not going to be so good for you. And we're going to talk about why as we get a little deeper in here. Before we go, a little bit of clarification. When it comes to talking about gases, we talk a lot about pressure. A lot of the other times in this semester we've talked about forces, but forces aren't a piece of vocabulary that works really well with gases. We're really going to talk about pressure, which of course is a force applied across an area. It just helps make things a lot more sense that way. When it comes to the units, pounds per square inch are the unit that we are going to use the most frequently. But there are other units of measurements that are commonly used, especially in scientific measurements when it comes to gases. Things like millibars or pascals. We're not going to get deep into those. We're just going to stick with PSI for the most part, since we're only going to be going into things at the conceptual level. And you'll be glad to know we don't really have any calculations this week. Or if we do, they're going to be extremely lightweight. The way that we measure pressure, one way, is with a barometer. A barometer is a very simple instrument, and here you see a schematic for just the simplest kind of barometer you can get. We have an open pan of water, and you can see that the atmosphere is pushing down on the water here. And then without a gap, you have this tube that comes up, and basically the higher the pressure pushing down from the atmosphere, the more water is going to be forced up through the tube. Now, the materials are different. It used to be that barometers were made with mercury, but mercury is not exactly the safest element to work with. It can cause poisoning issues. So a lot of barometers these days, kind of like thermometers, are made with alcohol that's been colored. When you hear the weatherman talking about the pressure when a new storm system's coming in, you'll hear him perhaps talking about how many inches of mercury. That comes down to inches of mercury, how far up the tube the mercury has been pushed in the barometer. Atmospheric pressure is what we're going to talk about the most because it's the best example of how different things work with gases. Similar to liquids, gases are pressing against you from all directions at all times, but the amount that they're pushing on you is not entirely constant. Anything that's below you when it comes to gases aren't really going to impact the pressure that you feel. And it basically comes down to the fact that gravity is working in your favor. It's on your side. If it's below you, it can't really push up against you very easily. The pressure that you feel from the Earth's atmosphere, also known as atmospheric pressure, is entirely the result of how much air is above you. And we're going to look at some simple schematics here to kind of illustrate that. On the left, imagine that you are standing on the Earth's surface and that directly above you there is simply a column of air extending all the way up to the edge of the atmosphere when it finally drops into nothingness, and we simply call it outer space then. All of the air that's in that column, gravity is pulling on it and it's pushing down on you as a result. That's what atmospheric pressure is. The weight of the atmosphere pushing down on you from above. Another unit, by the way, that you'll sometimes hear are just ATMs, 1 atmospheric pressure at the surface. Again, we're not going to get too deep into that. As gravity is working to pull down on all of the gases that are in the atmosphere, remember that gravitational force decreases the further away from Earth's surface you are. As a result, gases are going to tend to be more dense down here near the Earth's surface, whereas as you get higher up into the Earth's atmosphere, gravity is simply not pulling on them as much, and the kinetic energy in the particles is able to keep them further apart. And that trend continues all the way up. The higher you go, the lower the gravitational force, and the more spread out, the thinner or the lower density the gases become. And here again in the diagram you see that these are the molecules that are going to contribute to the pressure, the atmospheric pressure, if you are at this altitude right along the line. If you're at the surface, then you feel the force of all of these particles all the way up through the atmosphere pushing down on you. Now, atmospheric pressure is actually a really big deal, and I mentioned Mount Everest earlier, and let's talk a little bit more about that. The higher you go, the lower the density, and therefore the lower the atmospheric pressure is going to be. Our bodies are designed to handle pressures in a certain range, but when you start pushing that range, bad things start to happen. The average pressure at sea level from the atmosphere is 21.3 kilopascals. Let's go ahead and switch that over. That's really about 14 psi when you're down here at sea level. The higher you go, the thinner the atmosphere becomes. By the time you get up to Mount Everest, it's a third of that. So we're looking at 5 to maybe 7 psi of atmospheric pressure when you get up to the top. And what happens there is the atmosphere's density is simply so low that even though the oxygen percentage is the same as it is when you're down low at sea level, you simply can't pull in enough of the air to get all of the oxygen that you need. Things get dangerous. That's why if you are familiar with any kind of climbing, things happen at high elevation, and a lot of climbers use supplemental oxygen. On the airplanes, the reason they go through that safety announcement every time you fly is because if the pressure drops in the cabin, it's going to be extremely low air pressure up here. And you're simply not going to be able to breathe hard enough or fast enough to get all the oxygen you need for your brain to continue functioning. One of the things that did not really fit into the previous reading that you had this week regarding liquids is that in this way they're similar to the atmosphere, is that you're only going to feel the pressure of whatever amount of water is above you. So the PSI experienced by a diver right here is not impacted by the water below. It's only the water above that this diver is going to feel the pressure of. Now here's where we start getting into the next concept. You'll see that it's fairly obvious. The pressure increases as you go deeper and deeper into the water, in the same way that pressure increases as you are deeper and deeper in the Earth's atmosphere. Now what happens is, because of the increase in pressure, the volume of air can be compressed. And so here you see a simple graphic of how the volume of a gas changes with pressure. So every time you increase by 1 atmosphere of pressure, the volume of air goes down, 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 down. If you're familiar with any kind of scuba diving, then you may have heard of people getting the bends if they try and ascend through the water too quickly. Basically what happens is if you are at great depth and you try and get back up to the surface too quickly, your body has all of these gases contained in it, and it takes time for the volume of gas in your body to adjust to the pressures that it's feeling from the water out here. So if you rise too quickly, what's going to happen is the air in your body is literally going to expand too quickly, and that's going to do some bad things to your lungs and to your blood vessels, your entire circulatory system. It's not a good thing. This concept that as pressure changes, the volume has to change in response to it, this is known as Boyles Law. And it's a clear relationship between the pressure and the volume. They're inversely related, so basically as one of these quantities goes up, the other one is going to have to go down. If you increase the pressure, the volume by necessity will shrink. Same thing if you go the other way. If you increase the volume, it means the pressure is going to have to decrease. Now, they're tied to each other, and this is almost like a law of conservation. And here we just see kind of an equation form of what I was just talking through. We have the pressure that you start at and the volume that you start at, and those, if you multiply them, they have to equal the same thing that your final pressure times your final volume will equal. We're going to explore this relationship a lot more in this week's assignments, so I don't want to go too deep into this. But Boyle's Law is actually something that'll look kind of familiar if you have ever taken a chemistry course before. In chemistry, you may have heard what's known as the ideal gas law. Again, see this PV right here? That's very similar. That comes from what we just saw up here, that pressure and volume are tied to each other. There's some more stuff involved in that gets into a little bit of thermodynamics, and we're not going to cover that. Just wanted to point out that connection. One of the most fun applications of gases and the way that they behave is known as Benoullis Principle. Bernoulli discovered this a couple centuries ago, and the basic idea is that when the speed of a fluid, and a fluid can be either a liquid or a gas, when the speed of a fluid increases, the internal pressure of that fluid must decrease. But you'll also see this demonstrated really, really well in the other video required in this week's readings. So I'm not going to go into too much depth, but let's look at one quick schematic here. This is a whole idea behind how airplanes fly is Bernouilli's principle. As you're moving forward, okay, so the plane is moving from right to left, see the direction of flight, the air is going to be flowing relatively from left to right. As the air moves around the surface of the wing, it's forced to speed up as it deals with the curvature of the wing. So the bottom is a little bit less curved, the top's a little bit more curved. Here, the air speeds up. Because the velocity is increasing, the pressure along this red surface is going to decrease. As a result, there's actually going to be more air pressure underneath the wing than there is above it. So airplanes are actually being pushed up by the atmosphere as a result of Bernouilli's principle. Again, you'll see this demonstrated really, really well in the other video related to this week's readings. With that said, I'm going to go ahead and wrap this up. If you have any questions, please make sure that you let me know.